Hello everyone, my name is Aiden DiCarlo, and in this video I'll be talking about my final design for my seismometer for Europa. To reiterate from the midterm, the main mission of this project is to focus on developing aspects of a scientific instrument to be deployed on the surface of Europa, within the ice, or on a submersible under the ice. Out of the many good candidates, a seismometer was chosen. My personal design uses the property of electromagnetic induction by using a solid copper wire and neodymium magnets. Many components were created using SolidWorks, and the apparatus was put together using superglue. Due to high frequency noise produced by the electronics or extremely low frequencies produced by instrument drift and/or gravity field changes, the useful seismic frequency range of Europa was estimated to be 0.1 to 50 Hz. To ensure that these frequencies are not attenuated, a buffer of half a decade was applied to each extreme end of the frequency range, making the bandpass roughly 0.07 Hz to 159 Hz. Here's the rough list of materials used for the project. Several things have changed in the circuit design from the midterm. Most notably, there is an addition of the buffer amplifier. With this change, a common bias node of 1.65 volts of DC signal can be referenced for each axis of the non-inverting TIA input. This gets rid of two unnecessary voltage dividers, substantially cleaning up the circuit diagram. Additionally, the shared bias node across all three axes keeps the bias constant. Another change is the addition of an input resistor. Due to a limited selection of resistors and capacitors, a different amplification method had to be used. By adding an input resistor, the system now functions as a non-inverting amplifier with a gain of 1 plus the ratios of feedback resistor and input resistor. A detailed explanation can be found under the final report PDF. Additionally, the low-pass filter was removed from the design, as the feedback resistor and capacitor already create a low-pass filter. With all these changes, the full circuit diagram can now be sketched as such. These are the goals previously set from the midterm. Let's see if they hold up.
Go for it.
These are the results of a different set of shake tests, done with the same amount of force. When looking at the top graph, it becomes apparent that each axis was able to function individually when shaken in their respective axis. It can also be seen that on the fourth spike, the seismometer successfully plotted a chaotic motion across all three axes. For this, the result did in fact provide a visual representation of the vectorial changes in all three axes. As seen in the second clip of the demonstration video, as well as the graph from below, small shakes that only produced a hundredth of a volt was also recorded. For this seismometer had great success in demonstrating high sensitivity. Going back to the top graph, it can be seen that the highest peaks of the graph do not exceed 1 volt. This is expected as the gain of the system was designed for the voltage swing to range from plus minus 1 volt. With no clipping observed, the seismometer did not reach saturation. However, the frequency ranges experienced on Europa was never properly tested due to budget and time restrictions. This can theoretically be tested by using a platform shaker or a vibration generator. A good starting point in future generation models would be to get the adequate equipment needed for frequency testing. It would also be beneficial to adopt a 2-magnet flexure-supported coil system to cut weight and cost. This apparatus configuration is discussed in the PDF. Additionally, we can upgrade to a custom PCB to cut weight and cost. This concludes my presentation. Thank you.